Thank you, John. I'll be talking about the perspective of the water census, but this was supposed to be given by Jim Verdon, and I kept most of his slides in the back because I'm going to talk more about what I'm comfortable with, the technical aspect, how we create ET at USGS Aeros. So a bit of background, be showing some modest scale and ET anomalies for the corners, but also some earlier products using a Landsat scale, and some guidelines and specifications of what Jim Verdon is going to focus on. Yes, so what is water census? What is water smart? If I can clarify this, it would be good for a lot of you. We start working at the USGS as a water census, and then a few months later we were told we are going to use the water smart. So what the difference is, water smart is a DOI initiative, and water census is just a strategic objective of USGS, but it's really a subset of the DOI water smart. That's the overall objective of the water smart is to place technical information tools in the hands of stakeholders. So there are two primary questions about water use and availability. Does the nation have enough fresh water to meet human and ecological needs? And will this water be available in the future? At Aeros, the one I'm going to talk about is more of the demand and supply side of it, more of the consumptive use estimation. Because water smart involves Bureau of Rec. In terms of budget, the one we work at USGS Aeros is maybe 5 to 10%. Most of the budget goes to Bureau of Rec. So at Aeros, what do? We try to develop simpler models to improve the existing models for consumptive use estimation and apply this model in regional and national scales. This is obvious for a lot of you, so we're trying to answer this simple water balance equation. Mainly why it is important. One, it's driven by climate and management. That comes in the land cover aspect of it. But it's the most important, the most difficult component of the water balance. As you can see, this is in liquid form. The river flows in liquid form. ET is a gaseous form. It's usually estimated indirectly. Just to clarify the difference between water use and water availability. When we talk about water use, so that's the question to be answered is who is using or where is the water being used and when it's being used. So that's the water use aspect. When you talk about water availability, we may not care about who is using the water or when, but we want to know seasonally or annually the ET as a part of the overall water budget. So nowadays I'm becoming more comfortable to say it is one of the more, if not the most reliable remote sensing based products among the water balance components. So now there are remote sensing technology to estimate rainfall, like the NASA trim rainfall globally. You can use also remote sensing based storage like GRACE satellites, and also discharge this in future missions that's based on solving the Manning's equation. So of all these water balance components, I think we can say that the ET products are more reliable. If you compare trim-based station data, satellite data with station rainfall data, the scatter is all over. But the ET we get with flux tower data is more coherent and closer to what we believe is actual. I'm not going to go through the details of this. A lot of presentations have been made, but if you're trying to solve this, ETs from an energy balance, the land surface temperature is the most important one. There are different sensors. Landsat for a field scale all the way to GOES, what Martha Anderson is working on, 10 kilometer. If you drive this using a water balance, there is NOAA NEXRAD, a daily rainfall for the whole US at 5 kilometers, very good data set to run a water balance model. But if you want to go global, there are Meteosat and NASA trim at coarser resolutions. As I said earlier, if you want to do a water balance, we're just doing precipitation accounting. If you want to do energy balance, it's really the land surface temperature, the driving force. So if we want to do a water balance, we have a simpler model, a bucket model. But Jan said very nicely, I think this is going to be a second generation biophysical model, and we call it VGT. It's pretty much the FAO model. The difference, we drive this with precipitation and good soil stats going in the US. The difference we bring in here is the water use coefficient driven by the NDVI temporal pattern. And then it's a simple water balance bucket model. And this is operationally posted at our website. This is an example of as of September 22nd. These are wetter areas and these are drier areas. These are good for drought monitoring purposes and they're easy to run. It's automatic. The problem is this doesn't catch really the soil moisture condition in the Snake River Valley or the Central Valley in California. So for that reason, and these are the limitations shown by other speakers yesterday. We cannot monitor irrigation, subsurface water from by deep-rooted plants and forests, impact of pests and diseases. So for that, we go into an energy balance approach similar to metric. Well, actually, the idea came from metric, so I will give a lot of credit to Rick Allen. But whenever I present this in front of Rick Allen, I tend to get nervous. There's a good reason. So we drive this, really from the land surface temperature. Now we have incorporated some air temperature, and then we come up with an ET fraction. It's a very simplified version, and then we get a 0 to 1 fraction. But the magnitude is driven by the reference ET, as the idea from Rick Allen. So that's a hot and cold pixel approach. And I sent Rick, this is something, and I sent him the paper. He encouraged me to proceed this, but he had some questions and the accuracy of it, and we keep on discussing on this. I'll show you a little bit more how it works. So if you look at this graph, before we look at this is the evolution of the cold pixel in the bottom, and this is the evolution of the hot pixel. So every pixel will have its own difference between the hot pixel and cold pixel. That's the DT function. And it varies in space and in time. So seasonally, this DT function varies. So normally, Charles said, it depends on the person to select the cold pixel and the hot pixel. In this model now, where we call it SSEB, Simplified Surface Energy Balance Operational, what we do, we pre-calculate the DT. So every pixel will have its own unique DT. So which means it will have its own cold pixel and hot pixel, every pixel, anywhere. And we pre-calculate how do we solve that? Well, we solve the net energy balance for a clear sky, and we assume that everything is turned into sensible heat, and then we'll find the hot pixel in here. And the cold boundary condition is defined by the air temperature, because at the cold pixel, the air temperature and the land surface temperature become very close, so that there is no sensible heat. So with that, what you see in the green in here is just a land surface temperature. So you plot the land surface temperature and these predefined boundary conditions, where it lies, then it's a simple linear interpolation. What you see in here is a comparison with the flux tower. I think this is probably, I have to admit, one of the better results. Either we got lucky or there's something wrong, But it's hard to get lucky on 46 images, and this is a modest data. A similar approach, and here is in Oklahoma. Again, this is a cold boundary condition, predefined, and hot boundary condition, and this is a comparison with the model and the flux tower. And also, flux towers doesn't mean it's necessarily accurate. So this is the modest data. It's global coverage, and the other driver is the reference ET, the Penman-Monti reference ET. And this data comes from 6 hourly weather data from NOAA. And we solve the Penman-Monti, and it's very coarse. It's 100 kilometer resolution, but it works for homogeneous surfaces. As you can see, this is a pixel size of the GLDAS data, the weather data. And this is a comparison between a CMIS reference ET and GDAS-based reference ET. Now we're trying to improve this NLDAS using NLDAS data with 12 kilometers. Mike Hobbins is here. He's working on it. We'll talk about it later on more. So with that, we got some confidence, and this was applied actually for Afghanistan and a lot of Africa monitoring USAID project. And somebody said, well, can you do this in the US? So we did a preliminary study in the Columbia River Basin. So this was our ET estimation. Obviously, land surface temperature picks up the irrigated areas and the forested areas. And this is the precipitation, annual precipitation total. And we did a simple difference, and it shows you where irrigation is withdrawing water more than the rainfall it gets, and these are the potential recharge areas. So the groundwater available to people were very interested in it. They funded us a little bit, to do some more work. And Mali mapping is here, part of the water use product. So can you do this nationwide? So we applied this nationwide. This is the annual ET distribution for 2009 using MODIS data, a similar method. Obviously, you can get, well-vegetated rain-fed areas will get higher ET, but not only that, irrigated areas, including the Snake River Valley. So you can capture the ET, no doubt about it. But is absolute magnitude, good enough to pass the court of law? That's the thing, we need to discuss more. So we did this, all from 2000 to 2011. Similar spatial distribution, but the anomalies are more important for drought detection. So as you can see, satellite data being very consistent. Even if there is a bias in magnitude, it's consistent to itself, so you can trust the anomalies. So the 2011 drought, obviously, in Texas and Oklahoma was captured. The 2007 drought in eastern US, 2006 high plains. So in terms of drought monitoring, it's good. I think it passes the common sense test. And also this year, this is aggregation from April to September. So droughts were early detected by May, June. And this is a US drought monitor. This is a weekly product, but this is a seasonal product. So if there is a disagreement, that's just a different temporal scale. And we do this kind of product not only in the US. As I said earlier, the product was actually developed for monitoring developing countries where they don't have good in-situ monitoring systems. So this year, you can see the drought in a part of Kazakhstan, Russia. Just the same drought happened in 2010. And this year, actually, in Africa, northern the Sahel region is doing much better than a lot of other years. So as I said, water available, it's not only water used at the field scale, but we want to do this at a watershed scale. So we have been aggregating this data at different HAC levels. So this is an example being applied in the Flint River Basin in Georgia. And this is the prism rainfall. As you can see, there are 3 periods for the rainfall, and the runoff peaks in April. And nothing happens in terms of ET, very low ET. And then, a lot of rainfall in here. You can see the runoff is very low, but because of the deciduous trees, a lot of this water is turned actually into evapotranspiration. This helps you understand the water balance, what's happening in the basin. So comparison at water balance, so we're using the P minus Q as the truth, and this is ET estimated from the model, and this is for the Colorado, different HACs, for the Delaware, for the Flint. It doesn't work in all places the same way, but there is a very strong correlation between the water balance Q at annual basis, assuming storage change is 0, very good correspondence. In Colorado, there are some scatters. These are because of the irrigated basins that are not captured by the precipitation. So now we said, can we do the same thing on Landsat scale? So it seems like decent in MODIS. So we tried this in the Colorado River Basin being one of the study sites for WaterSmart. So this is a false color image of the study site, and this is run by MODIS, using MODIS. And so metric, we run also metric as a truth to see whether we are just trying, we're at least reasonably producing product same as metric. And this is the method we used. So these are spatial average. So maybe it's not fair. Spatial average things, tend to remove a lot of the noise, and we tend to get similar answers. But there is good spatial correspondence. So false color imagery, this is MODIS. I'm going to show you now same place with Landsat. Obviously, in Landsat, you will see the fields as stated earlier. But I think I'm proud to show, first time we managed to create Landsat for the whole Colorado River Basin. So what you see in here is the annual total ET for using MODIS. And same scale, now this is using Landsat. So in terms of spatial pattern, which means can alternatively use one or the other, of course, but the scale matters. Are you interested in basin-wide? Maybe you should use MODIS, but the field scale, Landsat. Getting a little bit zooming in, so this is a base map. You can see the vegetation here. This is MODIS, and this is Landsat. Similar products have been shown earlier, so just I would show you, so because I have them in here anyways. You see the fields in here. This is MODIS, much coarser, and Landsat. You see the definition. Again, center pivots in here. MODIS just smears it pretty much, and you can see individual center pivots in Landsat. And that Rick said, yeah, we will also model mountains, even if some of the equations fail. So we went up and just did modeling everywhere. And as you can see in here, some vegetation, and the Landsat captures it, and the MODIS. Okay, it shows some signal there. I'll show you some more of it. And this is a Landsat, and this is, MODIS pretty much loses it. Again, as you can see, there's interesting features in different side aspects of the mountain. Landsat and MODIS, there's not much signal. So there was a challenge from the Water Science Center in Arizona. Can you do golf courses? And same, without any calibration, we said, okay, this is just, then we downloaded this baseline. And this is the golf courses. You can see them from the baseline from Google Earth. And this is the AT we estimated. Is the magnitude right? I don't know, to be honest. We haven't validated this. But at least it captures, you can see golf courses use more water. And I think I can't trust this. One course is using a fraction of the other course. But is the absolute magnitude of that course right? I don't know. That requires more calibration. But the relative spatial differences, maybe difference between private courses and public courses, maybe we will be able to see that. So now, the question, how about other ET models? So the attitude of USGS, Water Smart, is of course, yes, all models that meet the user's objectives. This is just one model, simple model we produced. So there is a plan, is working with Utah State University with Christopher Neal, and Hatim is there. If some of you haven't met him, I'll talk a little bit more about that, to prepare guidelines and specifications on ET estimation. What do we mean by that? We acknowledge many prior and ongoing crop ET remote sensing activities by different states have been in place. Bureau of Reclamation uses its own. So the idea is potential duplication of effort. So there might be some duplication of effort, but people are comfortable with to use their own numbers. So the solution is, let's come up with a guideline and specification. What does it mean? What use model you like, and numbers accepted by the community, realized economies, but meeting certain accuracy standards. So Utah State University is organizing same data set so that to compare and validate different models. So we can use a crop location data layer from USDA, remote sensing data, the same land surface temperature in DVI, reference ET, grid reference ET. Rick mentioned the requirement for conditioning, and that has to be done properly. And then we want to work with other partners and produce daily ET at 100 meters. Is that the objective? So for now, the identification of currently available ET models has been already completed, review and testing of candidate models. So I hope your model is in here, or if it's not here, please talk to Hatim. So different models have been identified, some of them driven by thermal, reflectant-based. The idea is everybody will join in coming up with a specification guideline. Also, in terms of the reference ET, agreement has been reached between the National Weather Service and NIDIS to fund, develop, and implement a national reference evapotranspiration service using the NLDAS, about 12-kilometer grid data. Where is Mike? Yeah. So please talk to Mike Hobbins. He's working on coming up with gridded reference ET. So conclusion, I think for now, at least, successfully monitoring drought and relative crop performance is possible with our simplified energy balance model. Some of the indications are good. There is an operational product posted on the web. So we're trying to evaluate its accuracy and certainty level at MODIS and Landsat scale. But more important, specification guidelines are being developed. So hopefully all these modelers will participate in here actively. And I'd like to acknowledge the different people who contribute to this. And I'll be happy to take any questions you might have.
We have time for some questions. So, Bryce?
Your air temperature comes from ground data, or do you have a way of teasing that out of the remote?
Well, for now, we use the DAMET data. It's from a network of gridded from ground station data. That's what we use. But if an irrigation engineer wants to use a locally available weather station data that could serve a large area, you can use the station data you have.
Other questions?
I had a question on the determination of the cold,
Yeah.
the cold pixel temperature for each pixel.
Yeah.
You said that's based on the air temperature.
Yeah, a fraction of the air temperature. Yeah.
Fraction of the air.
Yeah. So what we do is, so we looked at, it's very stable throughout the season actually. When you look at well-watered, well-vegetated surfaces, you look at the air temperature, like say the maximum air temperature for the day, and the land surface temperature there. It's a fraction of the maximum. It's very consistent throughout. So we can use just a simple calibration. Maybe it's just 99% of at the Kelvin scale of the maximum air temperature. That will serve as your cold reference point.
So
It's
in a hot, dry environment, and the air temperature is affected by.
it's consistent. We looked at this is something individual user can test what fraction you should use, but it's very consistent and the standard variation is very small. It's in the paper just got accepted in JAWRA, and you can look at the paper. Thank you.
I think which you showed from the model is HMET, right?
8 day?
The models products,
Yes.
are they HMET actually?
Yes, indeed.
How did you estimate the crop coefficient? Perhaps you showed it, but I missed it.
Right.
The
So
crop coefficient, how did you calculate it with global scale?
right. So what we did, the crop coefficient is pretty much really the hot and cold pixel approach. So what we did is, we identified a cold pixel for every modus pixel, and we came up with what would be the hot pixel for that particular. If it was, for example, a well-vegetated surface, if you just clear it up and you have it bare ground over there, what would be the idealized, hot temperature over there? So once we have that boundary condition for the cold and hot, it's really the land surface temperature, the actual land surface temperature that gives you the KC, or in this case, the ET fraction. So it's really pretty much the same as CBAL and metric. I mean, the idea came from them, actually. So I will blame for those kind of things to Rical. I can talk to you later on, maybe. Yeah, sure. Yeah, you're in Nebraska. We're neighbors almost, so, I'll come and talk to you.